Yeah. All right. Good day, everyone, and you're welcome once again to this webinar. So, my name is Olawale Ibrahim, and I'm a machine learning and data scientist. Last year I won the first machine learning lithology prediction competition, and in today's webinar I'll be showing how we can prepare our logs to get optimal machine learning results. So, the scope of this webinar will be to use OpendTect Python tools to access database of wells, and how we can find wells in the database best suited for training and predicting on particular set of logs, and how we can prepare and train data with chosen machine learning algorithm, and also to compare and evaluate the results of different trained data extracted. So some of OpenTect Python tools include odpy, which is contains generic Python tools in OpenTect. It contains some modules like dgbpy, which is used for data access to the database in OpenTect, hdf5.py, which is used for loading saved models, and then wellman.py, which is used for access to the walls data itself. And then we also have dgbpy, which contains Python tools for connecting to the machine learning API in OpenTect, and also for making some visualizations, bokeh visualizations. So some of the modules include keras.py, which is if you're trying to make use of TensorFlow keras in OpenTect, it contains some useful methods in it. And then bokeh crossplot.py, which is used for making bokeh crossplots, and dgbpy if you want to make use of scikit line. You want to make use of scikit line in OpenTect to do some machine learning works. Also, on this webinar, I'll be making use of odpy.wellman, which is a module in odpy, which we'll be making use of for well data access. So some of the methods includes, which we'll also be covering when we get to the notebook section of this webinar. And some of the methods include get names, which is used to get the names of wells in the database, and get info, which is used to get information on for a particular well, and then get log names, which extracts and returns the names of logs for a particular well, and then get logs, which is used to get the log data itself, and then get well db list. So this returns a set of information on the database, which we'll also look at when we get to that section. So over here we are trying to find best suited training wells. So this stems from the fact that in OpenTect and in the database itself, there are large different number of wells in the database, different set of wells, different wells with different logs, and different from different environments. So for predicting a particular log or set of logs, it is very important for us to get the best set of data for training the model, so we can get optimal machine learning prediction results. So it's one thing to use all the walls in the database to train the model, which might be very time consuming, and then it won't also lead to a very good result, because some of these wells are not very suited for a particular it's not very suited for a particular log. So it's very important for us to extract wells well data, that is logs, and wells which are very similar to the well or log which we are trying to predict. So our approach includes to compare the wells in the database with the provided test well, so you can get the best subset of training wells, or wells which will serve as the training wells to train the machine learning model, so we can get very good results from it. So our method includes using statistical information of the provided data, that is the well, and then comparing it and the database wells. So we extract the statistical information of the wells and the database wells. So we're making use of we'll be computing the decimals to compare the data distributions of the well logs. A decile is a quantitative method of splitting up a set of ranked data into 10 equally large subsections. So deciles are computed by first sorting the data in ascending order, and then dividing the sorted data into 10 equal parts, with corresponding to a percentage increase of 10 percentage points. So over here we have the formula for we have a formula for calculating for computing deciles. So where I stands from I ranges from 1 to 10, which is the deciles which will be computed, and then n represents the total number of data points, the total number of data points. So to complete the first decile, it becomes d on 1 equals to, then substituting every other variable to get the first decile. So over here we have an example of some set of computed deciles for some particular data. We have the first decile up to the 10th decile. So over here we'll also be looking at this webinar. We'll also be looking at preparing and training the extracted data. So after extracting the best set of words which we think is the best suited words for training the machine learning model, then we'll be looking at interpolating the missing data present in the extracted word, and then training the model with an xgboost model. So an xgboost model is a chosen algorithm for training the data, and then we'll also be making use of a tenfold cross-validation training technique. That is to get very good results. So it's a kind of model improvement technique to get good results from the machine learning model. So and then after training and predicting, we'll be making use of this evaluation metrics, the root mean square error, which is a measure of how good the machine learning regression model is. So it's just a measure of how good the machine learning model is. So it compares the predicted values with the actual values, and gets the sum of errors. So the higher the root mean square error is, the worse the machine learning model performance, and the lower it is, the better our results. And also we'll be making use of the R2 score, which is the coefficient of the determination. So this is just a measure of how predictable a particular variable is compared in respect to a second another variable. So the value ranges from -1 to +1, and +1 indicating a very strong positive correlation, and the -1 indicating a very strong and negative correlation. So over here we have the formula for predicting the root mean square error. Like we said, it's the sum of the standard deviation of the residuals. And then over here we have a plot describing the root mean square error. So for some particular predicted values, we can see how they deviate from the actual points, the actual values, which is represented by this line of best fit. So now I'll be showing how we can arrive at all this, how we can use our method to get the data, and how we can also make use of OpendTect Python tools to perform this work. In the previous webinar, David showed how we can make use of Python environments from inside OpendTect. So in this particular in this webinar, I'll be using the jupyter-notebook to do the works. So I'll be launching that from inside OpendTect now, and then I'll be launching the prompt to start the jupyter-notebook. So now I'm going to navigate into the directory into the notebook which I created for this workflow, for this tutorial. All right. In this notebook, we'll be going through some of the things I mentioned in the presentation. So we'll be accessing well data from the OpendTect database, making use of odpy.wellman, and then extracting suitable words for model training, and then preparing the data before we move into the training itself, and then evaluating the predictions made. Like I mentioned, odpy.wellman is a Python tool. Is a Python module in OpendTect which is used to access the world's database. So we import odpy.wellman as WMN, and then we also import pandas and numpy, which we'll be making use of in this webinar. And then over here we have functions, which will be we have functions which will be used for computing the decimals. So each this function over here is for calculating each of the decimals, and then this function over here, the main decimals function, is a function which is the parent function which computes the actual decimals. So we'll be computing the first and to the ninth decimals for this work for this tutorial. And then so that's what so the function returns a result which is a computed data frames of the decimals. And over here we have some of the methods from Wellman. Like I said, we can make use of the get world db list to get information on the database, and then just checking to see what it returns. So it returns dictionaries, and we can check some of the keys of the dictionaries. So it returns the size of the database, world database, the IDs, the worlds are IDs, and the names of the worlds and status. So right here is just checking the names in the names of the worlds present in database. You can see we have quite a large number of worlds in the database, and then just checking the number of worlds, that is the number of names. So we have 108 worlds in the database. And over here is just making use of the get log names, which is to extract the logs present for a particular log names present for a particular world. So we are extracting for world 15914, and then we can see all the logs present for this particular world. So over here we make use of the get logs method, which is used to extract the world logs data itself, that is based on the logs which is passed as argument into the method. And then over here, so it returns on two objects, which is first the depth of the worlds, the depth data, and also the other logs present. Over here we can see the logs in form of a data frame, a table. And then just checking out our function, which is used for calculating the decimals. So the function calculates the decimals for each of the logs in the world, and then we can see that over here. And then we can see for the first to the ninth decimals for each of the logs has been computed. So the way the method works is, so for our test world, now our test world is world 15914. These are the computed decimals for each of the logs. So this same procedure, this decile computation is also done for every world in the database, and then they are compared, making use of the root mean. They are compared, each computed deciles for each logs is compared with each of the computed deciles for the training data in the database. So over here is just checking some of the missing values. You can see some logs have a very high percentage of missing values, about 80%, and then that is also reflected in how the deciles are computed. For example, the shallow resistivity log, you can see majority of the values are 0. That is the computed decile, and that is due to the missing values associated with the logs. So like I also said, we'll be comparing the computed deciles for the train and for the test world and the training worlds in the database, making use of this function, the check for correlation function, which computes the root mean square error of the computed deciles for the train and test worlds. So it returns a values of the computed root mean square error. So this is also just checking computing the deciles for the test world. So over here we import some other packages which we'll be making use of in this function. So this function is what ties and brings everything together. It's so this function is what is used for extracting the best or most suited training words based on the computed statistics. So it takes in the available names of the list of available words in the database which we've gotten, and then it takes in the test data frame which contains the logs which will be used for predicting the logs which you want to work with. So over here is just computing the test decimals. We are computing it again in this function, and then computing the decimals for every train. So we have a loop here which loops through the words in the database and computes the decimals for each of the logs and for each of the words in the database. So this function at the end of after computing all the decimals, it returns three objects. One is the data frame, which is the data frame of the computed decimals, and then the sum df, which is the actual the final data frame which we'll be making use of. So it returns the sum up rmse of all logs for each of the words. Okay, we'll be showing the results for that soon, so we can get that better. And also it returns the scaled data frame. So the scaled data frame is just really we do not want a particular or a single word to have a lot of effects on the final result. So we made use of a normalized. We find the normalized root mean square error, making use of the standard scalar from scikit-learn. So we have a chance that each of the logs are contributing equally, and no single log is having a kind of outlier effect on the final results. So while we extracted extracted the test data sets, and then we also extract the names of the words again, so that we can pass it into our find suitable words function to get the list of best suited words for the log. And since we are making use of so we are making use of the 341016R as the test data set. And since we are making use of it, and since this word is also part of the database, we have to remove it from the list of words which will be used for training the data set. So right here we make use of the find suitable words to get the best suited words from our method. And then, like I said, we have the first result, which is just the computed RMSE. That is the computed RMSE from the computed decimals. So after getting the sum of the root mean squared errors for the decimals, that is in the train and the test, comparing the train and the test word for each of the word, we can see it, and then the sum of the root mean square error for the decimals for each of the logs, caliper log and every other log in the test word. We can see the results for each of the logs, and for each of the words 107 words. So okay, over here we have the scaled data frame, which is just like making use of the normalized standard scalar which I mentioned previously to find the scaled sum of root mean squared errors. And then over here we have the final result, which is the sum results, which has computed the root mean square error of each of the computed decimals for each of the logs, and has summed all the errors together. So over here we we try to sort the root mean square errors. We try to sort the results that is starting from the list root mean square error. So from our method we are saying that this the top words in this result should be best suited for training our provided test word. So we'll be making use of this top words, the top 9 words to train our model. So they'll be divided into three portions. That is the first three words in this result will serve as a set of training data, and then the next 3 walls will serve as the second, and then the last 3, that is for the top 9 walls, will serve as the third training set. And they'll be making use of this training data sets to train the model, and then evaluate the results and see how they compare with each other. So from our method, we are saying that the top walls should have a better performance compared to the walls having a very high root mean square error from the computed deciles for each of the logs. So right here we have a function which makes use of Wellman to also get the data for the 9 walls which we'll be using. And then okay, so right here we made use of, so we created the 3 train data sets, that is for train 1, train 2, train 3. Make use of the top first to 3 walls, top first 4 to 6, and like that. So right here we checked on the shape, that is the size of the data set. So they're just about 60,000 and 40,000 and 32,000. So this is the first training data set. And then getting the, okay, over here we are getting the log. We are trying to extract the test data set again, and then just choosing the set of logs which we want to train our model on. So we are now making use of the coordinates to train the model. So we are dropping the coordinates logs, and then getting the actual logs itself, and then just checking to see the missing values in this flow. So there are tools in OpendTect which can be used to interpolate the missing values for each of the logs. But for this workflow, we made use of the mean values for a particular log to fill up the missing values. And over here we are importing the libraries which will be used for training the model, the xgboost model, the MS, the model selection model from scikit, and also a retrieval which we use for making the plots. That's for visualization. So right here we have the model itself. So in this model, we're making use of the train data set which we've created, and also the test logs to train the model and to make predictions. So we have some preparation in this in its functions which just tries to get the logs in the training data set in the right format, in the right sequence with those in the test logs, and then dropping column, that is logs in training data set that are not present in the test data set. And just some little preparation. So for this tutorial, we are making use of some logs to test the method. We are making use of the gamma ray log, the neutron porosity log, the density log, and the DTC log. So every other log in the data set will be used for training and predicting each of these logs. So we'll be evaluating the results, making use of the root mean square error, and then the correlation coefficient, which is the R2 score. So right here we are looping through each of the logs in the data set to train through it, then to predict, and also to evaluate. So we have the functions, the train method which is used to do that. And like I said, we are making use of a tenfold cross-validation technique. So it just has a kind of model assembled to get very good performance from a machine learning model. So we have some parameters specified: the number of estimators, the maximum depth, the regularization lambda, which prevents overfitting to get a good result, and also the co-sample by tree and subsample arguments, which also helps to prevent overfitting. And then the predictor method, which is used to make predictions from the 10 models from the cross-validation technique. And then the evaluator method, which evaluates the models based on using the root mean square error and then the correlation coefficient. So for the first training, we have for the first training data set, we have this result. So for each of the logs, that is for the gamma ray log, for each of the logs, the gamma ray log, it trains the model using the cross-validation technique 10 folds, that is 10 loops, and then it makes predictions making use of the trained models. And then same for the neutron porosity log and every other log which has been chosen as the test logs. So we can see that over here, and then we can see the visualization, that is the actual the predicted logs and the actual logs itself. You can see how it looks like. Same thing with the neutron porosity log, and then also the density log. So the same method is done for each of the train data set which has been created, and we can see the results. So for the first train data set, we can see the computed root mean square error for each of the test logs, and then the correlation coefficient. So same thing with the second train data set, and also the third train data set. So now we just we'll compare the results of the three training data sets, and I'll just okay. So like I said, from the method that is computing the test size and making use of the best the walls with the least root mean square error, is estimated that the top walls should have better performance compared to the walls appearing at the bottom of the of our results. So we can see from this result, the first this result over here is for the first train data set, which is a combination of the first three walls from the results, and we can see how it compares with the second train data set created, and also the third train data set created. So from the result, we can see the first train data set actually generally performed better compared to the second, and also the second performed generally compared to the third training data set created. So as we progress down the list of walls, the results generated, the performance is expected to get worse. So I think the main takeaway is that we've been able to make use of the computed cells to get the best set of training data set based on the root mean square the sum root mean square errors of each of the walls, and then we'll also be able to train our models with it and get some good prediction performance for the different train data sets. So in this tutorial, we've been able to make use of OpendTect Python tools. That is, in particular, we made use of odpy.wml to get well data from the database, and then also making use of the method to get the best suited set of training walls for training the machine learning model, and then evaluating the result of the different train data sets. So yes, I think that's that concludes the tutorial. If there are any questions, I would like to take them now. So thank you for listening.